Yeah, I'm trying to share.
This meeting is being recorded.
There you are. The floor is yours, Marcus.
No, perhaps I'm sharing. Let's see. So, yes. Hello, everyone. My name is Marcus Comstedt, and I'm going to give a very short presentation of a simple FPGA cartridge for the Commodore 64 and Commodore 128 that I've made, which I call the Orange Cartridge. So I'm going to jump straight in here and show you this schematic representation of what this cartridge looks like. So at the center here, we have the FPGA itself, which connects to every signal on the expansion port of the C64. And the FPGA I've chosen is a Lattice ECP5, which is a simple and affordable FPGA. And the nice thing about the ECP5 family is that it's supported by the open source toolchain called SymbiFlow. So you can actually create bit streams for it using only open source code. And this FPGA, like many other FPGAs, it can't use 5-volt signals directly. So there's also some level shifters down here, which convert the 3.3 volt signals from the FPGA to the 5-volt signals on the expansion port. Then there's some additional stuff to support the FPGA. We have some flash memory here for storing bit streams. There is 60 megabytes of RAM. There is a USB connector that you use for uploading new bit streams. And there is a micro SD card connector that you can use to load and save data to SD cards. And there is a push button and an RGB LED. There's also for debugging a JTAG interface and a serial port. And I also added, for good measure, a clock port connector so you can connect peripherals like the RRNet Mark III Ethernet module. Right, so moving on the top picture here, you can see the first prototype I had manufactured in August last year, just to test if this design could work at all. And it turned out that it worked just fine. So after trying out this prototype, I went to Kickstarter to see if I could interest people in maybe a manufacturing run of 50 units. Because when you manufacture electronics like this, the price per unit goes down a lot if you can make a run of something around 50 or 100 units. This particular board at 50 units, it comes to about 120 euros, complete manufacturing and the components and everything. So that's a sort of reasonable price for something of this kind. And apparently people thought so as well. So the Kickstarter campaign was successful. I got people interested in these 50 units. So now they are being manufactured in China by Seed Studio. Currently, there's a pre-production run going on right now. And I don't have the actual cartridges back from China yet, but this lower picture is what they're going to look like. So I made some minor changes from the first prototype. There's a bigger push button and LED for using the cartridge inside the case. And I added some extra GPIO connections for expansions, and the USB port has been changed from Mini B to a USB-C connector. Yes, so what can you do with this cartridge? Well, I'm going to show you a gateware project that I'm currently working on, which I call the RVCOP64. So the RVCOP64 is a RISC-V coprocessor for the C64. And to build this, I'm using something called the LiteX framework. And this is a Python framework, which allows you to take different modules and connect them together to form a complete system on a chip. So the LiteX framework provides you with some of these modules, and you can make your own. And one of the modules it provides is a 32-bit RISC-V processor called VEX RISC-V. So this is a 32-bit RISC-V processor. So the 64 in RVCOP does not stand for 64-bit RISC-V. It's a coprocessor for the C64. But it also runs at 64 megahertz, so it could stand for that as well. So this soft-core, this RISC-V processor, it runs at the same time as the 6510 inside the C64, and it can access the memory space of the C64 while the 6510 is running, and the 6510 can also access the memory space of the LiteX system on chip. In addition, the 6510 processor can control the RISC-V processor by, for example, accessing the internal CPU registers. It can halt it on single step and so on. So internally, it looks like this. We have this RISC-V core. The core has 4 kilobytes of instruction cache and 4 kilobytes of data cache. And if there is a cache miss, then there will be memory accesses that go out of the caches and into this bus interconnect, which is a standard LiteX component. And then there is on the other side of this, a 4 gigabyte address space, so 32-bit addresses, which is divided into different parts. So here we have, for example, memory mapped control and status registers, which give you access to peripherals, like, for example, the SD card reader. Then there is RAM internal to the FPGA, called block RAM. There's also some of that RAM is made read-only, so it's acts as ROM, and this ROM contains a BIOS for the RISC-V processor, which comes as standard with the LiteX system. And this BIOS has a command prompt that you can give some commands. Next area, we have the external RAM, 16 megabytes. And finally, there is a 64K region where you can access the memory of the internal memory of the C64. So any memory accesses that goes to this area turns into DMA cycles going down into the expansion port. From the expansion port, we can also get requests from the 6510, for example, for a low ROM. So here there's more internal RAM, which acts as ROM to contain some support code. And then you can get I/O accesses via the I/O1 range to CSRs that are explicitly for the 6510. So here we have to start with a virtual Uart. So it's a sort of fake serial port. And this is connected to another fake serial port, which is in this area, the controller states registers for the RISC-V processor. And here is where this command line interface of the BIOS uses. So by accessing this virtual UART, you can get access to the prompt of the BIOS, which I'm going to show you in a little while. Then we have this debug stuff where you can access the register contents and halt and single step. And then we have this part, which creates wishbone bus cycles. Wishbone is the name of the internal bus in the LiteX system. So from here you can make read and write requests to access, for example, the content of this 16 megabytes of external RAM. Right, so now I'm going to show you a demo of this running, if I can get it to work. And I have to apologize that this is not going to be a live demo. I did make an attempt to hook the C64 up and live stream it using a Pi KVM, but that didn't work out, so it's going to be a pre-made recording. Let's see, I'll stop this and yes, okay. So now when the 64 starts up here, we will see that this support ROM has added some extra commands to basic V2. And one of the commands is the terminal emulator, which connects to the virtual Uart. So here we get the BIOS prompt of the RISC-V processor. And we can look at what are the memory regions available. And one of these is the C64 memory space. We can access, for example, the border color register like this. And it also works in the other direction. So we have the rvpoke and rvpeek commands, where I can access the 32-bit address space of the LiteX system. In this case, it's the base address of the 16 megabytes of RAM. So we write some stuff into the RAM, read back, and we can also check it from the RISC-V processor. And there's the data. So what I'm going to do now is to load some RISC-V code from my floppy. And it's going to be loaded into the main RAM of the C64 to start with. And then from there, I'll transfer it to the external 16 megabytes of RAM and have the RISC-V processor run it from there. So I'm using the rv-stash command to transfer the data. And to the start of the external RAM. There we go. And then I'm going to load something for the 6510 to do as well. So this is a interrupt-driven SID tune that I'm loading. And I'm going to start it up. There we go. And then I use the rbsys command to start up the code I loaded for the RISC-V processor. So now everything on the screen is done by the RISC-V coprocessor, including the raster meters, and the top lighter gray raster meter shows the time it takes to actually render each screen, while the dark gray is the time it takes to push the pixels into the main RAM of the C64 over the bus. This quits after 2 revolutions. I'll just start it again. And as you can hear, the SID is playing, so the 6510 is running in the background. And actually, I have the basic prompt. I could give basic commands now if I wanted to, but I don't see what I'm doing because of the graphics, so I'm not going to. But as you can see, the processors run in harmony, so to speak. Yep, so that was the demo, and I should go back to the presentation. Let's see there, and yes. So finally, I'm going to show you some links here. First, the Kickstarter campaign. You don't have to write this down because the link is also on the Commodore user website. So the Kickstarter campaign is already finished, which means it's not possible to become a backer right now. I'm not using a pledge manager for this small project. But you can read all the updates. Everything is open to read. There are no backer exclusive updates. And if you think that you would like to have an Orange Cartridge for yourself, you can send me a personal message on Kickstarter. And then I'll know that I need to make some extra cartridges, because the main production run hasn't started yet, so it's not too late to add some extra. Then we have some GitHub repositories. First, there's the hardware, so the schematics and layouts of the cartridge itself is available as a KiCad project. So everything about this cartridge is open source. It's open source hardware, it's open source software, it's all the tool chains are open source. Then next repository is the RVCOP, the coprocessor. This is very much a work in progress, but you can see how it develops in this repository. And finally, because this toolchain is open source, it can be compiled for the Raspberry Pi. So I've actually prepared a SD card that you can run on the Raspberry Pi 3 or 4, which has all you need to compile the bit streams for the RVCOP 64 on the Raspberry Pi and upload it to the cartridge via USB. So yeah, that's what I had. Let's see if I can get back to this. Yes, and I'm back. Okay, that was it. Thank you. I think everyone has fallen asleep now.
No, I was just muted. And I have some echo here. Sorry. Unfortunately, my connection went down, so I went to an alternative 4G. So I did not. I haven't seen. Shit, I have more echo. Maybe it's muted. Do you also hear echo when I talk? Okay, don't know what's the reason. Maybe not anymore. Okay, no. So I lost actually the questions because
yeah.
So the only question I see is the one from Karen. How much? I think that's a question that many people can think about now. So how much is this? Is the cost for the cartridge?
Yeah. So it's going to be around 120 euros for the finished thing. And that's just for the mounted PCB, so it does not include the case. But you can use a standard case from individual computers, so you can 3D print one. I've made models for 3D printing.
Okay, and then I see, could this be used to create a super CPU re-implementation?
Well, absolutely. So if we look at the this RVCOP thing, that uses about a third of the resources which are available in this FPGA. So I think there's definitely room to make a super CPU.
Okay, nice. Can you show maybe, or do you have somewhere an inventory of the functionalities? Because of course I noted down the 16 megabyte RAM expansion, but is there some?
Yeah. So if you go to the Kickstarter campaign and you select the actual campaign page, then there you'll see this schematic of the different parts is there. The extra GPIO pins I added is not there because that was added sort of during the campaign, but it's the same picture that I showed here now.
Oh, okay. Okay.
Yeah. Someone is asking what is used for level shifting. So there's two different things. For the data and address bus, I'm using level shifters which are 8-bit parallel that can be where the direction can be shifted. They're called something 245 T8. But I mean, if the schematics is there on GitHub, you can look at them. But these are dual voltage supply level shifters. So you put 3.3 volt in on one side and 5 volt in on the other side, and then you have a signal to say which direction should the data go. Then for the other signals, they are either going from the FPGA to the bus or from the bus to the FPGA. And the ones that go from the FPGA to the bus, they are all open collector signals. So there it's actually a 5 volt tolerant open collector inverter that I'm using for all those signals. And for the ones that go from the C64 to the FPGA, those use a 5 volt tolerant Schmitt trigger. So none of those need to have dual power supplies. They are 3.3 logic, which is 5 volt tolerant.
Okay, thank you. I think that was answering the question. Yes, I see the comment. Nice, absolutely nice. Maybe one last question. I don't see more questions. Maybe if there were questions that I have skipped because I don't see them, then please either I would ask people to retype them or to just unmute and ask them. In the meantime, so the RAM expansion. Do you need something specific? Is there a specific mapping, or you use it? How do you make use actually of this extra memory?
Yeah, so to access the extra RAM from the C64 side, I mean it's connected to this internal bus of the Lytec system, so you can access it with this wishbone bus cycle generator. And the way that works is that you write the 32-bit address into 4 registers, and then you have a 5th register that you use to read data out or put data in. So you get sort of 1 byte at a time, and the address can be set to auto increment. So that is what this rv-stash command that I used, it uses that interface. But I mean, you can also, of course, have code running on the RISC-V processor, which transfers data for you. So from the RISC-V, you can just do a memcopy, because from that side you have, because the RISC-V has a 4 gigabyte address space, it can access both memories directly.
Okay, nice. I see another question from Karen. So I think it's still related to this the power and the level shifting. Are there any speed limitations?
Yeah, so I mean, all the signals which are on the expansion bus, nothing goes above 1 megahertz, right? Because the pixel clock is 8 megahertz. Everything else is on 1 or actually 2 megahertz, because there is the two bus cycles per clock cycle. But anyway, 8 megahertz is the fastest signal. That's the dot clock. And I mean, that's no problem at all. These level converter chips, they can handle tens of megahertz without problem.
Good. I see also a nice comment, Marcus. Also, thanks for all your other open source work. So maybe that's something you will come to another time to tell us about.
Yeah.
Good. I don't see any more questions. So I suggest then I will stop the recording. If some last minute questions come up, then people can still post them and you can answer them from the chat. Thank you very much, Marcus.
No, thank you.
And again, also thank you from the side from Hugo. Actually, it was really